Hello class, so what we're going to do today is we are going to actually see what the derivative is used for. So in the past we've learned how to find it, but now we're actually going to do work with it. And two of the things to learn in this video is how to recognize if there is an extrema on a graph, as well as finding critical numbers of a function. And we'll talk about what that means in a minute. Okay, so a local extrema is anytime I have a maximum point or a minimum point. So in a lot of our functions, we'll have, for example, in a parabola or in a sine wave, you're going to have these different parts of the curve. And anytime I have a maximum, we're talking about areas that have the highest point on the graph. So for instance, somewhere around here. Anytime we're talking about a minimum, we're talking about a minimum point on a graph. So we're going to find how to do this using a derivative, and they're pretty easy to find on a graph, but we're going to relate what it means when we're looking at these derivatives. So I have three graphs right here, and we're going to take a look at what's happening to the derivative for each of these. And so as a reminder, don't forget that the derivative is the slope of the curve as the slope of the line at a tangent point. So let's say I'm taking a look at this part of the graph. What would you say its derivative is, or the slope is? Well, if I draw a line tangent to that, I have a line that looks like this. And what does that look like? Okay, I'm hoping you said it looks like a horizontal line, and the slope of a horizontal line is 0. So if I were to line this up, I would say that f prime of 0, f prime of this point is actually equal to 0. So now let's take a look at the left side and the right side of this. If I took at the left side of this, I notice all my tangent lines look like this. What are the slopes of all those tangent lines? Good, they're all positive. They may not be the same number, but all I know is that they are all positive. Okay, let me make those a little clearer. Let's take a look at the other side of this graph. And if I were to put a marble, you notice the marble would fall down. Right? And if I take a look at the slope of all of those lines, I should get negatives. So let's take a look at what's happening at this graph. On this plus side, my graph is increasing. Aren't the y values getting higher and higher? So we're going to say this side is increasing. Increase. Okay, I don't have room for that, but it's increasing. And what would you say about the other side of this graph right here? It's decreasing, right? So this is decrease. I'll just put DEC. So that means something has to be happening at this point right here. And if you take a look, if it's going up and then going down, we're going to call this a maximum point. Okay? So let's take a look at another function right here. So if you take a look at this point right here, I don't have a horizontal tangent, but I do have this sharp turn, this point up at the top. It's also called the cusp. Well, whenever you have a cusp, my derivative is undefined. Okay? Because what's coming up from the left side and what's coming up from the right side, they have different slopes, so they don't match. So we say it's an undefined slope. But let's go ahead and take a look again at what's happening to the left side of this. And if you notice, this again is going upwards, and all the values are getting higher. So my derivative is positive on this side, and it's increasing, right? If I take a look at the other side, right here, the slope of my line is going downwards, And so that gives us a negative slope, which means I am decreasing. So once again, if I'm increasing and if I'm decreasing, what does this point have to be on the graph? Good, it has to be a maximum. So let's take a look at another graph right here. Over here, we have a sharp turn, and there is no derivative at this point. So once again, it's undefined. And if I take a look at the left side, every slope of the line, of the tangent line is going upwards, and every slope of the tangent line on this side is going downwards. And so if I were to take a look at this side right here has positive slope, which means it's increasing. This side right here has a negative slope, which means it's decreasing. And that means at this point, I have to have a maximum value. Good. So let's go ahead and take a look at the other side of this, which would be a minimum. So if I did this again, I notice right here, I have a slope of a tangent line that's horizontal, which means that slope has to equal 0, right? If I look on this side, my tangent lines are decreasing or have a slope that's negative. So I know this is negative, and I also know negative derivatives mean I'm decreasing. Oops. And so if I take a look at the other side, all my tangent lines are upwards, which means I am increasing right here. So that means I have positive slopes, and that also means I am increasing. Right here, I'm increasing. So what's happening at this point now is that I have a minimum. And if you were to predict these other two, and just by looking at the graph, in both cases right here, I have a cusp and a point. So let's actually call this one is a cusp, and this one is a sharp turn, which tells us I have to have undefined derivatives at those points. So UD and UD. And on this side, my slopes are going downwards. Same thing on this side. So if I have a downward slope, that means my values are decreasing. And that means these have negative values over here. Negative. And I'll say decreasing right here and decreasing right here. And then if I take a look at the other side, I notice that my derivatives or my slopes of the tangent line are all upward, which means we are increasing. And so all of those slopes are positive, as well as on this side. And I know this means I'm increasing here, increasing here. So at this point, or these 2 points, I'm going to have a minimum. So graphically, it's pretty easy to take a look at if it's a high point or a low point on a graph, but we're going to need to know how to do this mathematically using derivatives. So all of these points that we hit, this minimum, this maximum, this minimum, this minimum, this minimum, the maximum from the other page, these are critical parts of a graph. And so those are called critical numbers, and so we're going to see how to solve for these critical numbers using derivatives. So a critical number is when the derivative of a function is 0 or undefined, and this tells us that there has to be some kind of extrema happening there. So just to be clear, I'm going to take f prime of x and set it equal to 0. In case I do have a denominator and a numerator, this means for f prime of x, if there's a numerator and if there's a denominator, I'm going to take the numerator, set it equal to 0, and I'm also going to take the denominator and set it equal to 0. So we'll do two problems, one that does have a denominator, one that does not. So it says find the critical numbers of the function. And as the definition states, a critical number is when the derivative is 0 or undefined. So what I need to do is actually find the derivative, right? So let me move this up for a little bit. And let's go ahead and solve this. F prime of x is equal to 4x cubed plus 12x squared plus 8x. Alright, so I need to set this equal to 0. And the best thing to do is to start factoring. Okay, so let's factor this first. I'm going to pull out a 4 and then x, and I'm going to get an x squared plus 3x plus 2. If I take a look, I can factor this part a little more, and I get 4x times x plus 2 times x plus 1. Now that I can factor this, it actually makes it easier to set equal to 0. So I'm going to take this part, and this part, set those equal to 0. So let me scroll down just a little bit right here. And so I see that 4x is equal to 0 when x is equal to 0. X plus 2 is equal to 0 when x is equal to negative 2. And x plus 1 is equal to 0 when x is equal to negative 1. So my critical points, which I call CP, would be x is equal to the set, and I'm going to put them in order, so negative 2, comma, negative 1, comma, 0. So this function has 3 critical points in the graph. Let's go ahead and take a look at a slightly different one. So if you take a look at this problem here, you know it's a little more complicated because I have square roots, but I also have the product rule. So let's do the first term and the second term. F prime of x is equal to the first term times the derivative of the second is 4 times 2x minus 4 to the third, and using the chain rule, I need the derivative of what's in parentheses, so that's 2, plus the second term, 2x minus 4 to the fourth, times the derivative of that term. So square root of x is the same as x to the 1/2. So if I take that derivative, I get 1/2 x to the negative 1/2. Okay? So what I'm going to do is I'm going to rewrite these so that I have a denominator present. And if I do that, I get, just to simplify, I get 8 radical x times 2x minus 4 to the third, plus, I'm going to keep this on the top, parentheses 2x minus 4 to the fourth, bring this denominator down, and since this is a negative 1/2, I know there is a square root of x down here. Okay. So if you take a look, you notice I don't have common denominators, but in order to make this work, I should solve a little bit more and get these common denominators. So I'm going to multiply this side over here by 2 radical x. Let me just use a different color just to help you see that I'm trying to get these denominators the same. If I scroll down a little bit, let's simplify again. 2 times 8 is 16. Square root of x times square root of x is x, times 2x minus 4 to the third plus 2x minus 4 to the fourth, all over 2 radical x. So if you take a look, now that I have a numerator and denominator, I can set these equal to 0, but let's see what we can do with these a little bit further. Right, so I'm going to take this numerator part, and if you notice, this is why I always ask you not to simplify, because I can start to factor these terms out. I have a 2x minus 4 in both sides of this numerator. So let's pull one of those out, and I get 2x minus 4. But instead of pulling 1, I have 3 here and I have 4 here. So let's pull out 3 of them. And what's left over here is a 16x. And left over here is one set of 2x minus 4. Set this, make that down here. And now I have 3 things I can set equal to 0. Here's one parentheses, here's another parentheses, and then I have the denominator. So let's actually do this. Let me add a page in. Alright, so let's start with the first one. I get 2x minus 4 to the third is equal to 0. Well, what that does is gets rid of my power, and all I get is 2x minus 4 equal to 0. 2x is equal to 4, so x is equal to 2. It's one value. Number 2 is 16x plus 2x minus 4 is equal to 0. So if I simplify this, I get 18x minus 4 is equal to 0. If I move this over, I get 18x is equal to 4. And then if I divide by 18, I'm going to get x is equal to 2 over 9 if I simplify that. So x equals 2, x equals 2 radical 9, and the last set is 2 radical x is equal to 0. Divide by 2 and I get x is equal to 0. To undo a square root, I square these, and so I get x is equal to 0. So this right here also has 3 critical numbers. X is equal to, and if I order them, I should get 0, 2 over 9, 2. Just double check. These are my 3 critical numbers from taking a look at, from all these different pieces. So let me unsplit that screen. And that's the end of the section. So go ahead and take a look at these, and I'll give you a couple problems to work on in a minute. Thank you.